Hello wonderful person, this is Anton, and this is going to be a video that I've been kind of thinking of making for a while. Then I kind of stopped thinking about it and decided to just do it. And this is going to be one of the longer videos, mostly because of what's involved. So in this video I wanted to show you how easy it's become to go out there and try to find your own exoplanet. Okay, maybe not as easy as I'm making it sound, but it's still a lot easier than it was 10 years ago when I originally learned about it. And this is obviously using the very famous transit method that essentially relies on looking for exoplanets as they move in front of their star, leaving a shadow that you can then investigate. Now the reason it's become so easy is because of the incredible work that a lot of NASA scientists have done in creating a lot of very easy to use and very accessible tools such as this right here, Lightkurve, which is nothing more but a library that's available for the very famous programming language known as Python. And what this allows you to do is investigate all of the stuff you need to investigate very easy, very efficiently, and extremely fast. And so I just wanted to show you what you can try to do, and although we're probably not going to be finding any new planets just yet, I'm going to show you some of the planets we've already discovered, and also show you how you can take a look at one of many stars, specifically over 200,000 stars, that are currently being investigated by the incredible TESS telescope that's always sending us even more data, so you could be that one person finding a new planet. And so in this video I'm going to show you the tools, I'm going to show you the sort of the basics on how to do this. And I also figured it would be nice to have some sort of a discussion forum / community to talk about all of this. So there is a subreddit you can join if you'd like to, although honestly I'm probably not going to be looking into this too much, so this is really more for you wonderful people to go and share something you've discovered and possibly ask questions and ask for clarification. And possibly with time some of the researchers might join this as well, and maybe we can all just collaborate in finding even more planets than ever before. But if it doesn't work, it doesn't work. I don't really expect much to happen with this subreddit, and also I don't really use Reddit that much, so yeah. Anyway, what do we need to find all of this? Well, as I mentioned, we're going to be using Python. And Python is an incredible language. If you've never really tackled it to any extent, I highly recommend go and take a look at it. You can do so many things with Python, and it's a very easy to learn language. And for the purposes of this video, you don't really even have to know this much. You just have to understand one major concept. Python, like many other languages, is based on the idea of libraries. You can think of a library as a kind of a modification, like a mod that you add to your language to give it even more capabilities and even more commands. So here are the famous ones, like for example we have TensorFlow, PyTorch and OpenCV. Those are libraries for all sorts of deep learning and all sorts of AI algorithms. We have things like requests and Selenium, which are more or less tools to interact with the browser and the internet. And there are many more. It's almost 500,000 last I checked, but it's probably a lot more now. But for our purposes, we're only going to use, I think, 4 different libraries, or maybe 3. But really just this one, Lightkurve. Lightkurve was created by these wonderful people, and some of them are NASA scientists, so in that sense it's a very useful tool that's been used by many people already. And it also has a pretty amazing tutorial, which is what I'm going to be using in this video, but also we'll expand on this a little bit more. But I'm also going to make an assumption that maybe you have never used Python and don't even know where to start. So I highly recommend getting this, Anaconda. This works on pretty much every major operating system, and it's absolutely free. It's essentially a collection of various libraries pre-installed with Python, with the main purpose being this is an accessible way of starting with Python. This is exactly what I've used when I actually used to teach Python for many years. And since then it only got better. I personally am not going to be using this, but it's going to be very similar to what you're going to be installing here. Alternatively, if you already have a Microsoft account, like for example if you're using Windows 10 right now, you can also use what's known as Azure Notebooks. This is absolutely free to use as long as you have a Microsoft account, and it allows you to create all sorts of Python projects in the same way that I'm going to be doing here as well. But to make this more accessible and also shareable with everyone, I'm going to be using what's known as Jupyter Notebook. One of the reasons, of course, is that because it has the word Jupyter in it, so it is somewhat related to space science, but also because it's a pretty incredible tool. Jupyter Notebook allows you to run all of your Python stuff inside your browser. So that way you don't have to worry about command line or using any other tools. You can just start this in your browser and it works absolutely fine. So Anaconda, when you install it, already has Jupyter Notebook in it, so you can just start it right away. Alternatively, you can also just install this directly from the website itself or even try it in the browser. And the link that I'm going to be posting in the description that will have all of the code in it is actually going to be in Jupyter Notebook as well. And well, let's start step by step. And by the way, this video is going to be really long. I'm also probably going to be talking quite a lot, so my apologies in advance for making this too long. But then again, this is kind of like taking a month of lessons and trying to put them in an hour-long video. So if I do skip through some things and you don't understand them, or if I'm talking about something you already know for too long, feel free to skip or obviously ask more questions in the comments below. Now, when you finish installing Anaconda or Jupyter, you also need to download and install the library that we're going to be using. And essentially, after your Python installation, normally all you have to do is go into the command line if you're on Mac, on Linux, or open your PowerShell on Windows and type pip install Lightkurve. This command pip install is essentially how you can add additional libraries to your Python, but if you're using Anaconda, for example, there are ways for you to install this using user interface as well. I personally find that this is the easiest way to do it, and once you click it, and once you run this command, since I already have it installed, I don't have to do anything, but you'll probably have a bunch of stuff installing in the background. But if you're on Windows and for some reason you're getting, for example, command not found or some other error, what I recommend is just typing the exact error that you see into Google and then trying to figure out how other people solved it. Now, normally for a lot of people installing Python for the first time, this is sort of the main problem they encounter. So if you're struggling with this, I'll try to post something else explaining how to do this easier. For now though, let's assume you're done with the installation. You have Python installed, Lightkurve seems to have installed as well, and you can kind of start Jupyter Notebook as well. When you just start Jupyter Notebook, it's going to give you something that looks like this. There's going to be a bunch of files in the directory where it started, and you're also going to have this button right here that says New. All you need to do now is click on New and New Python 3 file. And if you see this, that's it. That's all you need. Now, just to test that all of this works, let's just run this command right here and find out if Python works. This is a print command that should be printing "Hello, wonderful person" if you click Run. Now, if you see this, everything's working just fine. And so now let's just jump directly into the library or module known as Lightkurve and start looking for planets. I'm going to rename this notebook into Lightkurve just so you can also download this for yourself later. And what I'm also going to do is just kind of explain to you some of the commands we'll be using. So the first one is going to look like this, and this is a typical import command. What import usually does in Python, and really in any other programming language, is that it takes the library that you have installed and adds it to your project. So in other words, until we actually run this command, we're not going to be able to use anything from Lightkurve. It's not available to us. But as soon as you add this line, you can now start using certain functions from the Lightkurve. And in this case, what we're doing is using something known as search target pixel file. Okay, so there's a lot of terminology that we're going to be using here, but I'm going to try to explain to you the best I can. So in this case, target pixel file actually refers to the pixels, literally camera pixels, produced by either Kepler or TESS telescopes. In other words, it refers to something like this, but even smaller than that. It essentially is an entire file through observations of a tiny piece of the night skies that either TESS or Kepler were looking at. For Kepler telescope, all of these files are going to be 5 by 5 pixels, so it's basically like a little square, all focused on a specific location, normally a star or possibly a galaxy. And each of these pixel files will be a collection of time frames. So essentially, for however long the telescope was looking at this location, it's going to have these pixels changing over time. Now, in this particular line, what we're doing is we're looking at a very specific location. It's the star with the designation 8462852. We're also looking at a very specific time, quarter 16, which is, what is this, like 4th year? Every year has 4 quarters. And this would make it 4th year, I believe, of the Kepler mission. And lastly, we're going to be downloading all of this. So to run this, instead of clicking run, I'm actually going to press Control Enter, and this will run this. And what it's doing right now is actually downloading everything in the background. If you get warnings like what I just got, just read what it says. And here it says, okay, because we have Kepler and TESS in our database, you have to choose which one you're looking at. This is actually from Kepler, and I know this because I've already looked at it. So we're going to add KIC to this and run this once again. This is actually from a tutorial on the website, and they haven't really corrected this, but this is essentially what's going to now download all of the data and create what's known as a pixel file for that particular star. Now, you might already guess what star this refers to, but this is actually one of the coolest stars that Kepler discovered. And now that the pixel file is loaded into your system, we can now take a look at it by using pixelfile.plot, and we're going to take a look at frame 1. This is the first frame in the pixel file, and it looks like this. So as you can see, okay, this is, I guess, not 5 by 5 as I promised you, but most of them will be 5 by 5. So what you're looking at here is the star that Kepler was looking at, and this is literally the best resolution we get from these stars. But it loaded a lot of frames here, so you can actually take a look at any frame you want. Like here's the 100th frame, here's the 1000th frame, and you'll notice that it does change with time. But this doesn't really help us analyze any of this. As a matter of fact, these frames by themselves are kind of useless. It's fun to look at them, but it doesn't show you what we can do with it. So we're going to turn this into a graph. We're going to combine every one of these into what's known as a light curve. Now, normally 10 years ago when I originally started doing this, it was super hard, at least for me. But in the last 10 years, a lot of new techniques were developed, and now it's as easy as writing a single line of command. The command that takes this pixel file and converts it into a light curve file. And that's essentially all we have to do. So now what we're doing in this command, we're creating a new variable or a new name. You can actually name this anything you want. This can be my star or something. And we're making it turn everything from this into a graph-like light curve. Now, once you run this, you're not going to see anything, but it's already done. So now we have something called LC. You can double check that it all worked by typing LC and running this, and it will tell you, okay, this is a Kepler light curve, meaning that it's a light curve from Kepler telescope. In all programming languages, these are what we call objects, and in this case, this object will have a lot of its own commands. You can actually find more of them by going to the Lightkurve website, which is also in the description, and looking at some of these tutorials here. For example, what are Lightkurve objects, what are target pixel file objects? But here, for example, the command time and the command flux will show you specific time of the observation and the relevant flux or brightness that the star was emitting. In other words, it gives you the digital version of this image that we have right here. But the most important command is lc.plot. Once we plot this, we get this. Now, can you guess what star this is and what this refers to? You might have cheated and looked at the tutorial already, but this is the famous Boyajian star, also known as Tabby star, also known as "Are those aliens?" star. So that's why the star created so much excitement and so many investigations, because there was a very unusual dip, right, like you see right here, and this kind of made no sense. And that was probably not a planet. And I'll show you what planets look like in a few seconds, but this is essentially all we need to do to recover data from Kepler telescope, create a pixel file, then create a light curve, and then create a kind of a plot where you can see if there's something going on or not. But let's also take a look at something that has an actual planet in it, so that we know what to look for. Because, I mean, if you just look at this, you're not going to know right away if it's a planet or something completely different. So we're going to create another pixel file. This time I'm just going to name it pixel file because we don't have that variable just yet. We're going to search for target pixel file with the name of the star KIC 69222244. And this is going to be in Q4 because that's exactly when this particular planet was already discovered. In other words, we're taking a look at something that we know exists for sure. We're not going to be taking a look at the pixel files in this case though, we're just going to directly convert it into the light curve. And in this case, it's recommended to add what's known as Aperture Mask, which essentially makes this look a little bit better when you analyze it. It's an advanced technique that's used in astronomy to make the image slightly better and essentially easier to analyze. But it's beyond the scope of the video. All you have to do is add it in brackets like this, and once you run this, oh yeah, I made a mistake, this was not named TPF anymore, it's now named pixel file. So once I run this, it creates a new LC, a new light curve, which we can now plot once again. And once you plot this, you get something that looks like this. And this is really interesting because you can definitely see something periodic is happening here, but at the same time the star is kind of dimming or something. Now it could be just a variable star that goes through periodic ups and downs. A lot of stars do that, except for our sun. Our sun is very mild in that sense. Although it could also be due to the motion of the telescope itself. And we can see that right here there's nothing. That's because the telescope was probably shifting or moving around. But this doesn't truly help us find out anything about this planet just yet. So we have to make this a little bit better. There are a few things we can do, very easy things actually. And they're only easy because the commands have already been provided for us. But number one, let's make this into a more flat graph, because it's a little bit difficult to analyze this if it's sort of shifted this way. So we're going to flatten this. The command for this is flatten, and here it is. We're going to create a new variable called flat_LC, and we're now going to plot that. And you can already see how this looks so much better. Something periodic is definitely going on here, and we can now even start guessing how often the planet crosses the star, and by how much luminosity the star brightness decreases, which will help us identify the size of this planet. But there's one more thing we can do to make this even easier on us. We know that there is a period here. In other words, we understand that the planet periodically crosses the star. So what if we took each of these observations and sort of folded it on top of one another? In other words, what if we were to somehow put each of these lines together? Well, there is a command for that as well, and this is essentially how it's usually done when you see the very beautiful image that shows you how a planet passes in front of a star. And so here, by using the fold command with a very specific period of 3.5225, which is actually how many days it takes for this planet to cross the star, I'm going to get this beautiful curve that shows you how the planet crosses the star, and this of course allows me to get a lot of data about this planet, including of course its size based on the changes in luminosity, and including some of the other additional information that some scientists can extract from this by looking at how fast this curve changes as well. And this is of course how a lot of those curves are reproduced in different papers that you might have seen in videos that I posted before. But the tricky question is, okay, but how would you know that period so exactly? I mean, just by looking at this, there's no way you can tell that this is 3.2225, which is where we have another interesting concept that we need to start using in order to identify how often these periods happen. But before I show you, let's just change the period just to see what it would look like if we were to fold it, for example, every single day. So period here is 1. Notice how the image produced makes very little sense. If we change this to 2, the image will be a little bit different once again. And if we change this to 3, I guess to some extent it's a little bit better, but still not perfect. So you do need to figure out how to find these periods. In astronomy, the way that it is done is by using a very interesting function or statistical analysis known as periodogram. The way that this works is beyond the scope of the video once again, but what it produces is essentially a frequency graph. A graph that shows you all of the possible repetitive patterns in your graph and then tells you which one is most likely to be the most periodic. Or to make this easier to understand, let's just run a periodogram function on this and see what we discover. But first let's import another library known as NumPy or NumPy. This is the mathematical library that's pretty much a must-have for any kind of a data analysis work. And also because here we can kind of see how many days it takes for each of these to occur, which seems to be maybe, I guess, under 10 days, we can change some of the values for this. And so here we're going to be looking at all of the possible periods from about 0.3 days up to 10 days with the difference of 0.0001 days. Once you plot this periodogram, what you get is something like this. This shows you all of the possible frequencies, with the highest frequency being right here. This is the most repetitive of all of the repetitions in this graph. And usually what this implies is that this is indeed the planet you were looking for. Here you can see that it's approximately 3 something, although here it's hard to tell, so we're going to run another command. In this case, it's a command known as period at max power, because this is the max power, and this will give us the best fit for this graph. And right away it tells you the best fit is 3.522. If you want this more accurately, you can change this to, let's just say, 5 significant figures, and you'll get the actual value. So now take this number and plug it back in here to get the folded version of this image once again. But there are a few more things we can do with this image to make this look even better. For example, we can use a function known as bin, and binning in this case is kind of like averaging out the values. In other words, instead of taking every single point, we're going to average out 10 points from nearby to try to see if this looks a little bit better. And notice how this kind of does look better. This is especially useful for some of the TESS data which can be very difficult to read otherwise. And one of the tutorials even has this line, which essentially does everything all at once. So it folds it for you, it does the binning, and it even removes any unusual parameters which are known as the outliers, thus creating this beautiful and very easy to read graph. And so that's the basis of looking for planets, at least for planets we've already found. But honestly, look through the tutorial section of Lightkurve, because they do provide a few more useful commands, especially if you're looking at something a little more complex. For example, in this tutorial they show you how to combine different observational quarters from Kepler to add it all in one single image. That way you can actually see everything all at once and possibly even discover a planet that has a much longer period that would have been missed otherwise. For example, another cool tutorial that they have is how to find and look at supernova and identify them when you actually see them. And the example that's used in the tutorial is Epic 212593538. Kind of looks like this, and here you can kind of see this is what a supernova might look like in the unprocessed data. This is actually an image from a galaxy, not from a star at all. But now let's try something a little bit more difficult. Specifically, let's take a look at the first ever TESS planet discovered only a few years ago, the planet around the star known as Python+. And the reason this is a little bit more difficult is because of the data processing that's going to be involved here. Actually, without the instructions provided by Lightkurve and by NASA, I don't think I would be able to see this myself. And here we're going to do this search a little bit differently, just so that you can see another way of doing this. First, we're going to create a variable known as search result, and we're going to apply this command to it, which now, instead of just the name of the star, also has the mission attached to it, and the sector where this star is located. Now, if you don't specify this, watch what's going to happen. Oh yeah, I forgot to do one more thing. I forgot to import the Lightkurve. So once we run this, as it searches through the catalogs, it discovers that there are actually quite a lot of different downloadable data available, specifically 8 different files. So it actually is going to ask you, do you want a specific quarter, campaign, or sector? And for the sakes of this tutorial, we're just going to use sector 1, where this star was discovered by the scientists. Now this created our pixel file, and we can actually check that this is the TESS pixel file. And we can even check which star this is going to be taking a look at. And if you plot this pixel file, it's going to look just a little bit different from the Kepler pixel file, but as you can see, it does have a lot more pixels and much higher quality. But once again, we don't really care about pixel files as much as the Lightkurve. So let's convert this to the Lightkurve, and let's plot this and take a look at what all of this looks like. So this is the star where the planet was discovered. And honestly, just by looking at this, I don't think I would be able to tell where the planet is. My instant assumption was this, but turns out that this is actually when TESS was moving a little bit. It was jittering, it was kind of not really stable, so that is not what we're looking at all. As a matter of fact, we're going to have to remove this part. This part will be cut from the analysis. But the tutorial recommends applying a different aperture mask to this to make this a little bit easier to see and a little bit easier to analyze, simply because of the amount of stuff that goes up and down everywhere. Now you can read more about different aperture masks on the website as well, on the Lightkurve tutorial website, but the idea here is that we're now going to apply this aperture mask to the Lightkurve to make everything look just a little bit better. Now this is a little bit better, but I would not have been able to do this myself without essentially reading about aperture masks for an hour. So this is something that you might want to experiment with if things don't look too good. But let's edit this a little bit more. First of all, what we're going to do is once again flatten this just to make it easier to analyze, but we also try to cut out this part because this seems to be useless to the analysis. This is basically the telescope moving around. You can also technically remove this part if you want, but let me just show you how to remove this first. I'm actually just going to copy paste this from the tutorial, so you can always go back and read more about this on the website. But this is first the flattening, and then here's how we're going to remove this part. So we're going to create a mask, and then we're going to specify the time for this mask. Everything that's less than 1346, so everything up to here, and everything that's more than 1350. In other words, the mask is going to include everything but this part. And then we're going to apply this mask to our original flattened curve, which will now basically result in this. This is missing, everything else is present. Another interesting thing you can do here is cut out some of these outliers that you can see here and there, which are actually easier to see if you change this to a scatter plot. Notice how there are certain dots here and there, which are basically outliers. They're not particularly useful to us. But when you change this to a scatter plot, especially if you make the dots very small, only 0.1 in size, you'll notice that there's something happening right here. Now this is that planet that they discovered. So let's see if we can maybe see this a little bit easier. Let's remove the outliers, all of these points here, and here you can modify how conservative you want to be about this. So that sigma level that you see in there refers to the idea of a normal distribution. This is that sigma, and basically here we have sigma 1, sigma 2, sigma 3. This level of 3 sigma refers to all of the points, approximately 99.9% of all of the points in your data. But if you go to sigma 5, that actually adds even more. In other words, you are going to be taking 99.999% of everything and removing the last outliers. In this tutorial, we're just going to use Sigma 6 because that's basically what the Lightkurve tutorial uses as well. And once you run this as a scatter plot again, you actually start seeing things even better. So you know that something is happening here. And so at this point, you might want to start folding your data just to see exactly what you're looking at. But once again, we don't really know how long this period is. We can, however, estimate it, and then use the periodogram we used before to try to see exactly where this period is located. So here we can kind of see that it's definitely less than 10, which means that we can use exactly the same periodogram command as before and look at all of the data between 1 and 10 in terms of repetitions. And here you'll see that right away this stands out. Whatever this is, around 6 something, is most likely what we're seeing here. And you can kind of see that this does actually seem to be around 6. But by once again running the period at max power command, we get the best fit period at 6.3 days. In other words, whatever this is, it's repeating every 6.3 days. Alright, let's fold this, and here you go. So there's definitely something happening right here. It is a little bit difficult to see though. But in the tutorial they use a slightly different period, which is why it's probably somewhat difficult to see this. So let's change this to what they have in the tutorial, and notice how right away it actually stands out a lot more. So this is still maybe a little bit too difficult to see, and there's still quite a lot of points all over the place. But one thing we can do here is use that bin command to average out some of this data. So here what we're doing is taking each of these points, and instead we're going to use the average value for 10 nearby points, which makes it look kind of like this. Now you can play around with some of these values, you can change the size of the points for example, to give it a slightly different look, but you can definitely see that there is something happening in this area. In the tutorial they actually used an error bar, which makes it look a little bit different, and you can also use the plot command to kind of see this, but I personally prefer scatterplot, because it does make it look a little bit clearer. And one more thing you can actually add here is you can shift this by just a little bit so that this part is in the center. This is done with an additional command right here, T0 equals to 1325. 1325 being this right here. So now if we run this, it's going to move to the middle, and all of this becomes a little bit easier to see once again. So that's essentially how the scientists got the data for Python+Lightkurve B, and of course how they were able to see everything. But that's of course discovering planets that have already been discovered. How do you find new stuff? Alright, so I know this video is probably already super long, but let's finish this. The most important part is, let's look for new planets. Which of course means not using Kepler data, because Kepler data is going to be very difficult to analyze. It's already been analyzed by all sorts of machine learning, all sorts of professors and students out there. Chances of discovering something new in Kepler data right now is pretty low. We can however find exoplanets in the TESS data, which is being updated very regularly and is going to be updated for many months to come. TESS's goal, by the way, is try to observe pretty much everything in the night skies with some exceptions. You can kind of see that there are some parts here that are going to be missing, but some parts are going to be analyzed very thoroughly. And it's going to be looking at over 200,000 stars, but the reality is that it's actually looking at several million stars, and also galaxies and a lot of other stuff, all of which is super exciting. And for this, we're going to be using the telescope database known as MAST. This thing has a lot of stuff in it. Even 10 years ago, when I just kind of started looking into this, you could pretty much access all of the data directly from the website. You still can, and it's still doable, but I personally find it very sort of tricky, and it's also really difficult to analyze things there, and it's not very fast. It's much faster to just download the data and do it with Python, which is exactly what we're going to be doing now. So don't forget, all of the links for this are in the description below, including the links for this, which is a planetary database that you can use to access or to check if certain planets were already discovered. Alright, let's do this. This is going to be the tricky part. Let's look for, I guess, all of the nearby stars close to our planet that are, let's say, are very specific in temperature. About 4000 degrees Kelvin to maybe 45 degrees Kelvin. In other words, we're going to specify a very specific window. Without this, it's going to be just overwhelming, and I'll show you why. We're going to click on the button here, select collection, and we're going to choose MAST catalogs. And here there's also more stuff, more different catalogs, but we really are going to be focusing on CTL, TESS CTL, and you can also use TESS input. CTL refers to the candidate target list, and these have been selected as the potential areas where we could discover some sort of a planet. And as you can see here, it actually already includes like 9.5 million stars. Which means that if this video somehow manages to get 9.5 million views, not likely. And also, if each of you picks a star and goes and takes a look at it and possibly discovers something around it, we might cover this catalog in no time. Yeah, let's hope this happens. Anyway, so now what we're going to click on is Advanced Search, and notice how right away it says we found 9 million something something record. This is all of the stars that it has in its catalog. So we need to kind of start narrowing things down, because we just want to download maybe 1 or 2 and do them one at a time. All of these are different filters, and you can technically just hide all of them first and then choose only the ones that you want to take a look at. Most of them will probably not make any sense to you, and they don't really make much sense to me either, mostly because I'm not really familiar with different types of magnitudes, for example. But what I want to take a look at is temperature of the star, which is T_EFF, and I want to take a look at very specific temperatures of between 4,000 and 4,500, and you'll notice that only 167,000 stars of this temperature were discovered. I guess we can also add metallicity, but we're not going to take a look at it. You can look at stellar radius, or the radius of the star. I just want distance. There it is. Distance in this case is measured in parsecs, and that's 3.26 light years per parsec, so you have to do some division. But let's just say, okay, within about, well, 32.6 light years, which means that within 10 parsec. Okay, within this distance, we're going to find, perfect, 7 different stars. So we have 7 stars of this temperature within this distance. Click on search, and you will get all of your stars in a window like this, where you can even take a look at each star and see what it looks like, in case you're wondering. So here's what each of them looks like. They're all going to be relatively similar. Oh, this one is cool. So now comes the tricky part. Technically, you could just take this ID and then just paste this in here, and hopefully it works in downloads. But the thing is, this hasn't always worked for me, and in a lot of cases it will say no data available because it hasn't really been processed, or maybe it just doesn't connect well. So this seems to not always work. You have to download these manually. At least that's what I'm going to do. So anyway, we can pick any of these stars. And if you're not sure which one to pick, you can also maybe go through some details. Go through, for example, what type of a star it is. I think this one is a dwarf, right? Yeah, it's a dwarf. And, well, you can kind of just pick one and see what you can discover. The easiest way to do this is copy the name of the star, then maybe double check it in ExoMask to see if anything has been discovered. This one says no planet found, which means that, well, so far no planet has been discovered here. But to download the actual star data, we're going to enter this name into the mass search right here. And once you search for this star, which by the way, in this case, I had to add TIC to it because otherwise it doesn't actually find it, we can see if there's any data that we can use to analyze this. Which in this case doesn't show us any TESS data, which means that it probably wasn't analyzed by TESS or hasn't been analyzed yet. Let's maybe take a look at the next star we've discovered on the list, which is this one right here. And in this case, once again, nothing. That's unfortunate. Okay, here we go. This is star number 4. We finally found one. Once you see that TESS has data, it's going to look like this, like a little red cup. And this is exactly what we want. Now, technically, you could just click on this and try to analyze this in your website, although I don't really recommend doing it this way. Instead, we're going to click on this, Download Data Products. And what this is doing right now is downloading all of the pixel files and all of the light curves already sort of pre-made for you to use in your analysis. So now what we have to do is just change one single line in our Jupyter notebook, and that line is, instead of downloading something, we're going to open it directly from a file. And now that the file has finished downloading, you're going to get something like this. Inside of this, there's a folder. You can open that folder, and this is where the 2 files that we need are located. There's the pixel file, or you can actually just jump directly to the light curve file. TP stands for, I think it's TESS pixel, and LC stands for light curve. Because all of our scripts so far use the pixel file and then they convert it to light curve, I'm just going to use pixel file here as well. So let's extract this to some folder somewhere, but make sure you know where you're extracting this, and also make sure that you can copy the name of this file. And here we're just going to change things a little bit. First of all, we're going to import another command called TESS target pixel file. I'm going to remove some of the stuff, we don't really need it anymore. We also don't need to really search for things or download them. And the next thing we're going to do is create a new variable called TPF, which is target pixel file. Here, TESS target pixel file command And here in brackets, we're putting the destination to this file. Now, in my case, it's this. In your case, it's probably going to be something a little bit different. Like, for example, if you're on Windows and you download this into downloads, it might look something like this. Either way though, once you run this, it should tell you that this is a test target pixel file. Just to check that everything works, let's just plot this. Okay, it's showing us some sort of a star here. We can also maybe apply an aperture mask. We don't really know if we need it yet, but we're going to use it anyway just to make things a little bit easier later. And now we can just kind of scroll up and use the same commands we've used before. So for example, let's convert this to a light curve and use a scatter plot. We'll get something like this. Okay, well, that looks interesting. And by the way, this is the first time I've ever seen this star and possibly planet. And well, there might be something going on, but we need to flatten this. So I'm going to copy and paste the flatten command to see what this is going to give us. And also maybe change the scatter plot to look a little bit different. And okay, well, there's something going on. I don't really know if this is a planet though. It's very difficult to see. So we might want to modify this a little bit, play around with some of the data here. But honestly, right now, I'm not really seeing any specific dips. But I'm still gonna try. Let's see if we can actually find anything. So far I'm not seeing anything. Let's maybe, just in case, run a periodogram just to see if we can maybe fold this on a certain period to see what's going on there. Oh, by the way, make sure to change the actual names. Make sure that this is a correct name. This is from the previous example. In this case, we now have flat LC. So I'm going to change this to flat LC. And also maybe increase the period to about 30 days just in case. Okay, let's take a look at the periodogram. So there's something here, and this seems to be the strongest period, but I don't know if this is a planet. Nevertheless, let's fold on this period because this is the highest one we have. But first, let's find out what this period is by using period at max power. It's going to tell us it's about 12.223 days. And I guess there is nothing planetary looking here. Yeah, this doesn't look like a period of a planetary passage, at least to me, at least right now. One last thing we can do here is average out the values, and here we're going to do the binning process, which gives something like this. So there's something happening, but that's not a planetary passage, and what we're most likely seeing here is the natural variation inside the star, which seems to be happening every, 13 something days. Yeah, 12.2 days. And here it's kind of visible as well, so these are not planetary passages probably. And we can even see them in this image here. But just to make sure, you can also fold on different periods. Like for example, maybe find out what this period is, which I think is around 3 or 4. You can also fold on these other periods to see if you find something else. But honestly, from this image alone, it becomes kind of obvious that it looks like there is no planetary passage, but it looks like the star just has a natural variability. It's a variable star like so many stars out there. And just for fun, I used the Hipparcos name for this star, which is right here, to discover a little bit more about it. And yeah, it doesn't seem to have any planets. It's also known as Gliese 884, and nothing particularly exciting has been found about this star. So this is just an example. And obviously, because we actually looked at the stars relatively close to planet Earth, it's also very likely that most of these stars have already been sort of searched through. But there are so many other stars to discover and so many stars to look through. Which is kind of why I wanted to create this video, and also wanted to show you how to do this, and then also give you a chance to maybe share your discoveries or possible questions, concerns, and so on by using this Reddit right here. And honestly, this is really just for this video specifically. So if you want to share what you discovered or possibly have questions about how to discover things, post them right here in the Reddit. Hopefully we'll have a community going where people will help you with this. I'll personally try to answer as much as I can, but because I'm already trying to catch up with my comments on YouTube, it's sort of becoming a little bit difficult. My apologies if I can't answer everyone. Either way, I really hope that this video helped you at least get started with all of this planet research, and most importantly, I hope you learned something in the process and you know how to search for planets yourself. Remember, by using the advanced search here on MAST, and also by using very specific filters, like for example, stars of specific size, stars of specific temperature, specific distance, maybe stars that are similar to Sun or very different from the Sun, or by even specifying the location or any other specific feature you would like to focus on. And by the way, I'm posting the basic tutorial for how to use this in the description as well. You can then really narrow down all of your search to just the stuff you want to see. And then possibly discover a planet somewhere out there around a star that nobody ever has taken a look at. Now, honestly, if a lot of people do this, chances for new discoveries are pretty high. And now that you have the right tools and the right knowledge to try to do this yourself, I mean, there's no one stopping you, right? It shouldn't really take too long, and you can find all of the files and of course the Jupyter notebook file with all of the code and all of the information in the description below. But also let me know in the comments below if you did discover something, possibly post a link to it or to the Reddit itself. And by the way, I've done a few other programming tutorials in the past, and the one that I would recommend you watch if you want to learn a little bit more about Python is the Kerbal Space Programming tutorial, where we go from complete scratch, from nothing, to a self-landing rocket that kind of mimics the SpaceX rockets. Not to the extent where it lands on the platform, but all of the code there shows you how to create everything from automatic takeoff to automatic navigation to automatic landing. So this tutorial I was actually really happy to make, and if you'd like to see something else similar to this, let me know in the comments. On that note, go out there, find some exoplanets, and post the links for your discoveries in the comments below. Best of luck to you, thank you so much for watching, subscribe if you still haven't, maybe share this with someone who loves learning about space and sciences, maybe come back tomorrow to learn something else. And if you've lived through this long video, congratulations, you now get the imaginary sticker that says, I did it, I know how to find exoplanets. I'll see you tomorrow, space out, and as always, bye bye. Oh yeah, and I forgot, if you'd like to support this channel, there's always Patreon, or you can buy the Wonderful Person t-shirt you can find in the description. Well, that's about it. I'll see you tomorrow.